I would like to introduce you this paper titled Outlier Robust Sparse Estimation via Non-Convex Optimization. This paper was published in September 21. So let me please show you the guide of this presentation. The content is going to be first, I'm going to introduce the motivation, what's the problem this paper tried to solve, then the main contribution of the paper, the methodology, how it works, how we solve this task, and some experimental results from simulations they do to evaluate the performance of the estimator. So this paper explores the connection between outlier robust high-dimensional statistics and non-convex optimization in the presence of a sparsity constraint. They present results for two tasks. One is the task of recovering robust sparse mean estimation, and the other one is robust sparse principal component analysis. In these presentations, I will focus mostly on robust sparse means estimation. So they develop a novel and simple optimization formulation of these problems, such that any stationary point of the associated optimization problem yields a near optimal solution for the underlying robust estimation task. That means that with simple methods, we don't get like bad local optimals. So it's overall achieves near optimal solutions. And the corollary of this that any first ordered method can efficiently convert to stationarity yields an efficient algorithm for this task. So let me please present the motivation of the problem this paper tried to solve. So the basic setup is there is a set of ensample G star that is a collection of points xi. This point xi I taken from a distribution from the family of distribution D that belongs to the reals in the dimensionality of D as well, since are points vectors of D entries. We have a collection of n of these points. And one property this paper assumes is that this G star sample is K epsilon delta stable. That means that for any weighting vector omega belonging to a simplex delta n, we're gonna explore what that simplex is following. But for any weighting vector omega, we have that the weighted mean, that's mu under W, is not too far from the true mean. That is if we evaluate an L2 norm for a K sparsity vector, it has to be less than delta. And also the covariance, the weighted covariance matrix evaluated using the Frobenius norm for the K bigger points in this K sparse vector has to be less than delta square over epsilon to the identity matrix. The other quality this problem has is that we are talking about epsilon corrupt samples. So this G star sample can be adulterated, like modified by attackers in a small fraction, let's say epsilon fraction. This epsilon observations n can be replaced for new observations in a product for an attack, for instance. And this new sample, the corrupt sample, epsilon corrupt, is called S for us. So the main goal or the main problem we are analyzing here is the problem of recovering K sparse vector mu hat that is sufficiently close to the true mean mu. The main contribution of this paper is, as I told you, to propose a novel non-convex optimization formulation for the task of robust sparse mean estimation and robust sparse principal component analysis, and establish results showing that any approximate stationary point of these objective functions yields a near optimal solution. The main contribution for the specific problem of robust mean estimation can be summarized in this theorem 1.2. It says that if we take a epsilon small between 0 and 1/3, we have a G star sample with this K epsilon delta stable property we talked before. It's K stable in relation with a distribution with an unknown K sparse mean mu belonging to the reals of dimensionality D. And let S be this epsilon corrupt version of G star. Hence, there is an algorithm that on input S, K, epsilon, and delta runs in polynomial time and returns a vector mu hat such that mu hat is not too far, is less than O delta in L2 norm from the true mean. So that's the main contribution of this paper. Now, please let me show you how it proceeds or how they find the solution to this problem. And the idea is to formulate a non-convex optimization problem that finding the mean of this corrupted sample is equivalent to the problem of minimizing the weighted variance of the samples. So we define a function f of w. W is a weighting vector, and we were looking to minimize the Frobenius distance between the covariance matrix of the weighted sample with respect to the identity matrix. We are doing that imposing the restriction that the weighting vector omega has to be into the n epsilon simplex. The epsilon simplex is an vector omega weighting vector belonging to Rn such that this vector adds up to 1, so it's a weighting vector adding up to 1, but each weighting point has to be between 0 and 1/1 minus epsilon n. That's a restriction we have. We don't want to put too much weight on some vectors, so we put like we're bounding below 1. The covariance matrix omega, the covariance matrix is just the sum of the weighting distance from the weighted mean, and the weighted mean is just the mean of the samples weighted by this vector we are looking for. So the solution is looking for a vector W such that the weighted empirical mean is close enough to the true mean. The idea is that this algorithm is trying to weight heavily on the good samples and put less weight on the bad samples. And if we're thinking in terms of outliers, let's think like the outliers that are too far from the real distribution gonna produce like a higher variance. So the intuition behind that is that if we want to reduce the variance of the sample, we are weighting less the outliers and more the observations that are into the main distribution that we are looking for. And this problem, as we told before, can be solved by any first order optimization algorithm like gradient descent. So the algorithms propose the similar steps. First, we have the data that requires like a value k greater than 0. That's the sparsity of the vector. A fraction epsilon of corrupted sample. This has to be bounded for less than 1/3. This epsilon corrupted sample must be drawn from a distribution with a k sparse mean mu. The result is a vector mu hat that is close enough to mu, and we find this vector mu hat by first finding a vector omega into this simplex and epsilon such that minimize the distance in Frobenius norm between the covariance matrix of the weighted samples and the identity matrix. that is only looking at the k biggest points in this. So that's the notation, the Frobenius norm in kk. That's the sparsity, but in the square space here. So this is the main result. We're going to review like 3 experiments that, so there are 3 different models of corruption of the data that the authors provide. The first one is the linear hiding node. We're not getting into the specific, but it's a corruption model. And they compare it again, different algorithms for recovering the mean. The first one, the blue one, is the oracle. That means will be the truth in some cases. We're informing the algorithm what are the corrupted samples. We take out these samples and compute the mean in that case. So that will be like the true sample mean we're looking for. The robust mean estimation of Sparse is like a previous result of 2016, is one of the well-performing algorithms. This is the main comparison point, I will say, from this for this paper. This paper is the Sparse gradient descent, is the red one. And then we have the naive pruning, that is like removing the epsilon fraction of outliers, and the random stack is removing a random sample without putting any weight on the quality of the samples we are taking out and computing the mean. So these are the main algorithms we're comparing, and we can see here that when we increase the number of samples, all the algorithms overall perform better in L2 loss, but especially for small samples, this Sparse gradient descent has a very good performance, even better than our benchmark, that is RMESP, the purple one. And we can see that when the number of k, the sparsity is relatively small, it's also like well performing, very close to the oracle. Here we have a different contamination process, the tile flipping noise. We can see here that the distance between the sparse gradient descent and the oracle, that is like the ideal benchmark, let's say, and the red one, the black one is the empirical benchmark, but this is the ideal benchmark, like if we knew the true samples. We can see that the distance is constant even when the sample increase, and in this case is reducing when the fraction of corruption increase. This is the epsilon. Here we can see that again the distance is still constant between the sparse gradient descent and perform equally well than the benchmarks, the oracle and the RME, but compared with the ransack and the naive pruning, it performed much better as the sample size increased, because the loss is increasing for the other, and in this case is increasing exponentially when the number of sparsity increase. So we can see that overall the algorithms do what they are looking for, and the experimental results are near of the theory, what they say, and in comparison with other algorithms, is perform equal or even better in some scenario. So, well, thank you very much.